The date is April 11th, 1970, and outside of the Kennedy Space Center, three men sit atop millions of pounds of explosive fuel. American astronauts James A. Lovell Jr., T. Kenneth Mattingly II, and Fred W. Hayes Jr. have been safely sealed into the crew module of their Saturn rocket 45 minutes ago and have spent that time strapped into their seats, awaiting the long list of final checks required before launch command is given. At last, Flight Control receives the all-clear from dozens of different department heads whose jobs are all to ensure a successful launch. And at 2:13 p.m. Eastern, the massive Saturn rocket roars to life. Almost 5 million pounds of fuel ignite, and the mighty Saturn slowly lifts off the launch pad, gradually increasing speed. In moments, the crew is already breaking the sound barrier, roaring into the heavens on a mission for the next manned landing on the moon. The rocket is a multi-stage vehicle that conserves fuel by gradually shedding spent stages and thus lowering the total mass that needs to be lifted up into orbit. This allows the Saturn to achieve the fuel efficiency required to bring significant loads, such as the Apollo spacecraft itself, into orbit. But it's not without its risks. According to the plan, the first stage burns for 2 minutes and 41 seconds, shooting the rocket to an altitude of 42 miles at a speed of 6,164 miles per hour. At that point, explosive separators would disengage the first stage from the second stage, shedding tens of thousands of pounds of dead weight. The second stage's 5 engines would then flare to life, accelerating the spacecraft for 6 minutes to a height of 109 miles and 15,647 miles per hour, which is almost orbital velocity, or the speed needed for an object to remain in orbit. Then the second stage would separate, and the third stage would fire to put the spacecraft on a parking orbit around the Earth. At that point, the Apollo Command and Service Module would detach from the third stage, turn around and dock with the Lunar Module, which was secured right below the CSM during launch, and extract the Lunar Module from the spent third stage. All of this required an incredible amount of careful engineering, and with millions of moving parts, anything could go wrong at any time. For the astronauts of Apollo 13, though, those first few seconds after engine ignition were the most terrifying, as all aboard knew that if the engines failed while they were still only a few feet off the ground, the entire rocket would come crashing down, and the millions of pounds of fuel would incinerate everything. In fact, the fully fueled Saturn vehicle could release an energy equivalent to 2 kilotons of TNT if it failed at liftoff, giving the astronauts on board no chance of survival. Yet today, the rocket seems to be working fine, and in moments the crew is breaking the sound barrier and speeding toward their first stage separation. Almost 3 minutes later, the crew hears the explosive bolts fire off as the first stage is successfully cast off, and a moment later they're kicked back into their seats as the 5 engines of the second stage fire off. Carrying a much smaller payload, the engines quickly accelerate the spacecraft, pinning the astronauts to their seat. Yet in what would turn out to be a precursor for the doomed mission, the center engine suddenly shuts down as alarms ring both on the ground at mission control and inside the command module. Unbeknownst to the engineers on the ground and the astronauts aboard, the flight computer has automatically shut the engine off due to several oscillations caused by uneven burn of that engine's fuel. If left unchecked, the uneven thrust could produce even more severe oscillations, which could lead directly to mechanical damage and possibly outright destruction of the engine. Luckily for the crew, though, the computer has detected the pending problem and shut the engine off just in time. But even more luckily for the crew, the afflicted engine is the center engine. Had it been one of the 4 outboard engines, the spacecraft could have tumbled out of control. At the speeds Apollo is now traveling through the atmosphere, that would have ended in certain death as wind resistance shredded the spacecraft. To compensate for the loss of the center engine, the computer replots its flight profile and burns the 4 outboard engines for longer than planned. As the second stage separates and is cast off, the third stage's single engine burns longer than originally planned as well, to compensate for the lost engine in the second stage. And though fuel margins are incredibly tight, luckily the spacecraft has enough fuel to compensate for the emergency. Well over 100 miles over the Earth, the spacecraft is now in a parking orbit, and the crew runs system checks and prepares for their burn window to send them to the moon. When some final checks sound the all clear both on the spacecraft and on the ground, the third stage begins its translunar injection burn. After a successful burn sets Apollo on a non-free return orbit to the moon, meaning the spacecraft won't simply swing by the moon and be pulled back to the Earth. The command module separates from the third stage and, as planned, spins around to dock with the lunar module, which is then released from the third stage. Moments later, the command module makes a small burn to alter its own trajectory. The original translunar injection burn has put the third stage directly on a collision course with the moon as part of an experiment that NASA plans on conducting. The third stage is plotted to impact within just a few kilometers of where Apollo 12 had deployed seismometers, with the resulting seismic shock giving NASA scientists insight to the inner structure of the moon. The astronauts are now safely on their way to the moon and broadcast live to the world below. After their brief TV broadcast, the astronauts remove their heavy pressure suits and settle in for the long 3-day ride to the moon. Their goal is the Fra Mauro Highlands, a region fraught with hazards as it's rather hilly and will make landing challenging. Yet the site promises to hold a treasure trove of geological data, as it's full of ejected debris from the impact that had formed the huge Mare Imbrium lava plain, the remains of one of the largest craters discovered in the solar system, and the iconic large dark spot visible to us every night on the moon's face. 30 hours into their flight, the astronauts light up the command module's engines for a small mid-course correction in order to fine-tune their final orbit around the moon. All is still well aboard the spacecraft, and on the ground all systems are reading green. The historic mission is set to be the success that all of the USA's previous moon landings have been to date. 56 hours into the mission, Apollo 13 is 205,000 miles from Earth. The astronauts have just ended a live TV broadcast and are stowing the equipment when flight controllers ask command module pilot John L. Swigert to turn on the stirring fans inside the hydrogen and oxygen tanks in the service module, which would help them get even more accurate readings on their levels. 2 minutes later, there's a large bang, and the electrical power inside the command module begins to fluctuate wildly. While outside the spacecraft, the attitude control thrusters fire briefly, in what have become the second most famous words ever uttered in space. Swigert radios home, saying, "Houston, we have a problem." Electrical power is slowly being drained from the service module, and oxygen tank number 2 reads completely empty. The astronauts are confused and initially think that they may have been struck by a micrometeorite, not realizing that one of the oxygen tanks has exploded. On the ground, NASA technicians and engineers have been recalled to mission control from home and their offices, the situation already looking dire. 3 minutes later, 2 more fuel cells fail, plunging power levels in the service module to critically low levels. Outside the window, astronaut James Lovell can see that the spacecraft is venting gas into space, likely oxygen. Over the next 2 hours, the main oxygen tank also depletes until finally running empty. The crew is in serious trouble and desperately needs a way back home. Lead Flight Director Gene Kranz officially orders an abort of the mission, and engineers on the ground begin scrambling to find a way to provide enough power to the remaining fuel cells to save the astronauts' lives. With the service module, which was meant to return the crew to Earth, out of commission, the flight engineers fall back on an abort plan originally drawn up in 1966, but never actually put into practice or even tested. The crew will shut down all systems aboard the command module completely and move into the cramped lunar module, which they'll then use as a lifeboat to get them back to Earth. Designed for only 2 astronauts, the ride is not going to be comfortable for the 3-man crew, but it's the only chance the crew has to get back home safe. The original plan for an abort, though, had called for the jettisoning of the lunar module entirely and burning the command module's engines at exactly 60 hours flight time in order to achieve a free return lunar flyby. However, the crew would die without the lunar module, so the planned burn is scrapped. With the moon's sphere of gravitational influence just a few hours away, flight planners have to work fast to figure out a way to bring the crew home using the lunar module. Yet there's another critical problem to solve as well. The lunar module was designed to sustain 2 people for a day and a half, not 3 people for 4 days as it now needs to. The spacecraft still carries plenty of oxygen, as the lunar module had to repressurize after each EVA on the moon's surface, but the lithium hydroxide, which is critical for removing carbon dioxide from the atmosphere, is in short supply. Most of the lunar module's lithium hydroxide canisters are stored on the descent stage and out of reach of the astronauts, who cannot conduct a spacewalk to retrieve them. If a solution is not found swiftly, the crew will asphyxiate long before returning to Earth. The command module has enough lithium hydroxide stores to safely clean the crew's air supply, yet the CM's canisters are cube-shaped and the lunar module sockets are cylindrical. As NASA engineers go into a flurry of brainstorming to figure out a solution, Flight Control works on figuring out a safe return trajectory for the stricken spacecraft. Flight Director Kranz orders the crew to burn the lunar module's descent engines for 30 seconds. This will allow the spacecraft to slingshot around the moon and be hurled back to Earth. And after a second burn on the far side of the moon, Apollo 13 would be on its way for a splashdown in the South Pacific. But if the crew can't breathe, all the US Navy would be recovering from the spacecraft are 3 perfectly preserved corpses. Inside Mission Control, NASA engineers furiously work at solutions to the lithium hydroxide problem, gathering together a store of all materials available to the astronauts themselves. With just hours of clean air left, an ingenious solution is found. The crew is ordered to cut off one of their spacesuit's air hoses using tape, Velcro, and other odds and ends. Fashion it into an adapter for the cube-shaped lithium hydroxide canisters from the command module. Much to everyone's relief, the improvised solution works brilliantly, and at last the crew of Apollo 13 sees some real hope of returning to Earth safely. Yet the crew is not out of the woods yet. To conserve very limited power supplies, most of the lunar module systems and all of the command module's computers have been shut down. This means temperature control as well, and the plummeting temperature has the crew shivering. Even more dangerous though, condensation has begun to form on the inside of the stricken spacecraft, and there are serious concerns that when the command module is powered up, it will cause catastrophic electrical shorts. To add to the astronauts' worries, the command module was never designed to be completely shut down in flight and then restarted. With time running out and power at too low of levels for a normal power-up routine, Flight Controller John Aaron and astronaut Kenneth Mattingly, who was originally supposed to be on board, work with engineers to figure out a way to restart the power-hungry command module with the limited power supply available. Working tirelessly and without sleep, the ground team manages to figure out a way to restart the CM systems while avoiding unnecessary power draws. With the Earth in their sights and re-entry just a few hours away, Apollo 13's crew begins to power up the CM per Houston's very careful instructions. Back on Earth, the ground team holds its breath as Apollo 13 systems come back online one by one, and then explode into cheers as the command module comes fully to life. Yet, as the Earth looms large before the astronauts, one final challenge remains. The lunar module must be safely separated from the command module before re-entry, or both vehicles will burn up in the atmosphere. Typically, the service module's reaction control system would fire off a small series of thrusters to gently pull away from the undocked lunar module. Yet the power failure has left the RCS system inoperable, and the now useless service module was going to be released before the lunar module anyways. On the ground, NASA engineers, in conjunction with counterparts at the University of Toronto, conclude that the only way to separate the command module from the lunar module would be to pressurize the tunnel connecting the two just before separation. And once separated, the rush of gases venting into space would push the lunar module away. Yet the ground team has to carefully calculate the exact pressure required to do so, as too much pressure will damage the command module's hatch and seal, leading to the astronauts burning up in the atmosphere. Too low pressure would not push the lunar module far enough away, putting the two craft at risk of collision during re-entry. Using just slide rules and with 6 hours before atmospheric re-entry, the ground team, led by Bernard Etkin, work furiously at their calculations. With an hour left, the exact figure is radioed up to Apollo 13, and the astronauts seal the hatch to the command module, venting oxygen into the tunnel that connects them to the lunar module. The astronauts hold their breath as they prepare to undock, knowing that if the calculations are wrong, they are certainly dead men. And with no way of averting atmospheric re-entry anymore, they'll have a long time to think about their certain death. At last, the lunar module is undocked, and with a hiss of escaping air, the vented oxygen successfully pushes the lunar module away to a safe distance. Apollo 13 would go on to splash down just southeast of American Samoa in the South Pacific. Easily the most harrowing mission ever undertaken in manned spaceflight. Apollo 13 may have been a technical failure, but was a complete success in testing mankind's ingenuity and resolve in the face of incredible odds and adversity. More than a successful mission ever could have, Apollo 13 proved that mankind truly has what it takes to make the bold move into space so vital for our shared future. Even if, sadly, just a few years later, the United States and other nations of the world would seemingly lose all interest in ever visiting the heavenly bodies above us ever again. If you enjoyed this video, I suggest you check out our other video, Why You Could Never Be an Astronaut. Thanks for watching, and I'll see you next time.